Hey folks, welcome back. So as promised, I got a couple more examples using conservation of energy with work. I've rewritten the equation here. If you need to pause the video, you're welcome to and recopy the equation down, but you can just use the equation you had written on the previous video as well. Um, so I got three more examples for you. So the first examples in the previous video were examples 1A and 1B. So the first example, I'll call it 2A. Okay. And what we're going to have here is we're going to have a repeat of an example we had when we didn't have friction. And that was a spring pushing a mass along the ground. So let me kind of redraw that. I'm going to move this down a little bit. All right. So let's say you have the floor here and a wall, and you have a spring against the wall. And let's say you have compressed the spring 50 centimeters, and it has a spring constant of 1,000 newtons per meter. And you put a book up against the spring, and the mass of the book is 2 kilograms. Okay. And then you let the book go. Okay. Now, in the previous example we did, when we didn't have friction, we had this thing on wheels, and we figured out what velocity will this book have when it leaves the spring. And just for reference, I'll write that number down off to the right here. We had a velocity of 11.2 meters per second. Okay. Well, now we're going to add friction. So let's say that there's friction between the floor and the book, and that force of friction is 15 newtons. Okay. So for part A here, what we're going to figure out is when the book is leaving the spring. So when it's traveled the 50 centimeters that the spring was compressed and it's leaving the spring, how fast is it going now? Now, by the way, how should that number compare to 11.2? Well, probably going to be a little less because we have friction acting on this thing now. It's trying to slow it down, okay? All right, so looking at our conservation of energy equation up here, okay? We'll call this point A and we'll call this point B. So point A is when the book is pressed up against the spring and the spring is compressed, and point B is when the book is flying away from the spring. So at point A, does the book have any motion? Well, no. So it doesn't have any kinetic energy. Does it have any changes of height anywhere? Well, no. So there's not going to be any gravitational potential energy in this problem at all. Is there any compressed springs at point A? Yes. So we've got an E elastic energy, 1/2 kx squared. There is a force that's going to do work and change mechanical energy into heat, and that's going to be friction. So we have our W term. Okay. And then when the book is leaving the spring, what kind of energy does it got? Well, again, the spring's not compressed now, so there's no spring energy anymore. There's no changes in height, so there's no potential energy. But the book is moving, so there is kinetic energy. Okay. All right. Now for elastic energy, the equation is 1/2 kx squared. The work done by friction is going to be negative because as the book moves right, friction is going to point left. So we've got minus force of friction times delta x, and that's going to equal the kinetic energy of the book, which is 1/2 m velocity squared. And now remember, on your sheet, you're going to have these three steps you always got to do. So here's step one, here's step two. Step three is, sub in the numbers we've got. So we got 1/2 k is 1,000, and x is 50 centimeters or 0.5 meters, and we have to square the 0.5. The force of friction I gave you to be 15. Delta x is also 0.5. It's how far the book is moved. 1/2, the mass of the book is 2, and then v squared. Now we're just plugging numbers in. First number is 125 minus 7.5. 1/2 of 2 is 1. V squared. So v squared is going to be, let's see here, 117.5. And if you square root that, your velocity is 10.8 meters per second. So it's going a little slower than it would have without friction. Without friction, we had 11.2 in the previous video, and now we got this frictional force acting in here. Now it's 10.8. Okay. All right. So that's example 2A. Now, example 2b is much shorter. Okay. Example 2b is when this book leaves and it's moving at 10.8 meters per second, how far is it going to slide before it comes to rest? And let's assume it's the same frictional force of 15 newtons acting on it. So basically in this picture up here, there's a third spot, and that's way over here when the book stops. We'll call that point C. So now we're going to look as the book travels from point B to point C. And we're going to use our conservation of energy equation again. And again, I want to calculate how far does the book go before it stops. All right, so looking at our conservation of energy equation up here, at point B, is the book moving? Well, yeah, it's moving at 10.8 meters per second, so it's got kinetic energy. Is there any height? No, so there's no potential. Is the spring compressed at all at point B? No, so there's no spring energy. So I can write EK for kinetic energy. Friction is going to do work on it as it slides from point B to point C, so I'll put W friction. Okay. At point C, looking at our conservation of energy equation, is there any kinetic energy? Well, nope, the book stopped moving. I want to know how far it goes before it comes to rest, so it stopped. There's no height, so there's no gravitational potential energy, and the spring is not compressed again, so there's no elastic energy. So what kind of energy does the book have when it gets to point C? Well, the answer is none. In other words, all this kinetic energy is going to turn into heat through friction against the ground. Our equations then become 1/2 mv squared minus force of friction times delta x equals 0. I'm going to sub in all my numbers. 1/2, the mass was 2. Our velocity was 10.8 squared. And then I'm going to move this other part of the equation to the right side. Friction is 15, and we're trying to solve for delta x. And if we do the math, we plug this in and then divide by 15 and solve for delta x. You get delta x is 7.83 meters. So that is how far the book will slide before it comes to rest. Okay. All right. And then our last example, we'll call it example 3. Okay. Let's say we have the ground and you have a big old box. Box has a mass m, which I'll give you in a minute. And let's say you are pushing the box forward. Okay. Now I'm going to give you a whole bunch of data here. Okay. So let's say that the mass of the box is 20 kilograms. Let's say at the beginning here, it's already moving. Its velocity is 2 meters per second. Let's say you push the box 5 meters, okay, and so that it gets to here, okay. Let's say you are pushing with, we'll call it an applied force. Now you could also call that a normal force, by the way, but I'll call it an applied force of 100 newtons. And let's say friction is also acting on this thing, and friction is acting with a force of 40 newtons. And what I'd like to know is at the end of the 5 meters, how fast is the book or the block moving? Okay. All right. Well, I'm going to draw a little FBD here to kind of remind me what forces are acting on the book. I'm sorry, on the block. So you have your applied force, force applied, which is 100 newtons. You have friction, which is less, which is 40 newtons. You're going to have gravity, which we could calculate, but we don't need to. And we have normal force, which again, we could calculate, but we don't need to. All right, now there's more force acting with the book than against the book's motion, so the book is going to speed up. So our final velocity should be more than 2 meters per second, okay? Well, let's do our conservation of energy equation. So at point A, so oh, and by the way, I'll label these up here. So let's say point A is at the beginning and point B is at the end. At point A, is there any kinetic energy? Well, of course there is. The book's moving at 2 meters per second. Is there any potential, gravitational potential energy? Are there any changes in height? No. Are there any springs in this problem? No. Okay. Is there any work done by forces that are not involved with the spring or height? Yes. Now here you're going to actually have 2 works. You're going to have the work done by the applied force and the work done by the frictional force. So we have to actually have 2 W's in the equation. Okay. At point B, does the book have any kinetic energy? Well, we think it's moving, so I'll put an EK there. Does the book have any gravitational potential energy? Well, nope, there weren't any changes in height. And does the book have any spring energy? Nope, well, there was no springs involved in this problem at all. So there's our equation. That would be in your first box on the worksheet. In the second box, we plug in our number or our equations. So we have 1/2 mv squared. The work done by the person, okay, is that positive or negative? Well, this force is with the motion, so it's plus Fa delta x. How about the work done by friction? Is that positive or negative? Well, that force is against the motion, so it's minus force of friction times delta x. And then we have 1/2 mv squared final kinetic energy of the book. The third box you plug your numbers in. The mass is 20. The beginning velocity was 2. Got to square that. The applied force was 100. The distance we traveled was 5. The frictional force was 40. The distance we traveled is 5. And then we have 1/2 the mass of the block, which is 20. And then we're trying to solve for the velocity at the end. We start plugging our numbers in. This first number is 40. The next number is 500. The third number is 200. And then 1/2 of 20 is 10. And we have our v squared. And so doing the math, you get 340 equals 10 v squared. V squared is going to be 34, and v is going to be the square root of that. And if you square root that in your calculator, you get 5.83 meters per second. So again, all the 3 steps you want to do on these problems are write out the conservation of energy equation, what terms actually make sense in the problem, plug in the equations for each of those work terms, and then substitute your numbers and solve for what they're asking for. All right, good luck on the practice sheets.